So since the test is coming up so quickly, I'm thinking I'll print all the formulas on the test again. It's kind of sad, but I guess we'll do that. Because after today's lesson, you're going to find there's kind of plenty formulas. Well, when you see today's lessons. Okay, so we just have to go over a few, yeah? Yes, who has the homework already? Negative 3 plus 2 sine theta. R equal negative 3 plus 2 sine theta. So since this number, the absolute value of this number is bigger than that one, it's going to be the monopua, right? But you really don't have to know that. You just plug the 4 quadrantal angles. So if you plug in 0, you get negative 3. If you plug in pi over 2, you get negative 1. If you plug in pi, you get negative 3. You got to go on the opposite side now. And if you plug in 3 pi over 2, you get negative 5. 1, 2, 3, 4, 5. And so it is the monopua. That's it. Let's plot the 4 quadrantal angles for the limos on S and D. S, R2, okay, so X. R equal 2 over, I forget already. Is it this? Oh, cosine. Okay, well, the base, okay, you know what this does, right? It rotates it pi over 4 clockwise. So first you got to get the base graph. This is the base graph. How do I draw this? Cross multiply, and you get R cosine theta equals 2. U somebody, X equals 2. So it's just a vertical line, right? So 1, 2. It looks like this. Okay, now you got to take this and rotate it 45 degrees counterclockwise. So now this distance is 2. So if you rotate it counterclockwise, this distance still has to stay 2 now. So it looks like that. Like you're just rotating it 45 degrees above the origin. So like this distance is still 2 now, because that's 2. So just rotating it 45 degrees counterclockwise. And then V. Wait, R equal 2 sine 3 theta. Gosh, I forgot already. Pi over 3? Okay. So first you take the base graph. This is V, yeah? 2 sine 3 theta. What is this? It's a rose curve with 3 petals. Right? And since this is a sine one, you set the argument equal to pi over 2. So theta equals pi over 6. So 1, 2, 3, 1, 2, 3. 1, 2, 3, 1, 2, 3. So the first petal is going to occur at pi over 6, and they're all equally spaced apart. So it looks like this, right? Ah, that's not like that. June. Okay, now you take the graph, and then we're going to rotate it pi over 3 clockwise. So that means this petal is going to go up here. This petal is going to go over here. And this petal is going to go over there. So everything gets rotated pi over 3 clockwise. So now the graph looks like this. So, yeah, so all this thing does here is just rotate the graph. Yeah, that's all it does. So you get the base graph and just rotate it. Any others? I guess not. Okay. Now today for homework, okay, since we're probably pressed for time too, I'm just gonna do problems from the homework, and then look, your homework, you have a reduced homework. And I even took out stuff, so it's like you don't even have to know stuff that they have to know the last 25 years. Plus you're gonna get formulas. Well, Okay, so first thing. So what are the ways that we know how to graph right now? Change it to a rectangular equation like today's quiz, right? And hopefully you know what that graph is. Or you have to just memorize certain ones that come up often. That was last night's homework. And then tonight's homework, last resort, you just gotta plot points. That's what you gotta do. So polar 3. Okay, who has polar 3 up? Okay, number 1. Number 1, here, polar 3. So you have to do B, I'm gonna do A, and you don't have to do the other two. 1A, R equal, gosh, I forgot what it is, cosine squared theta. Now, I even gave you directions. Plot a point every 45 degrees, and then that's probably good enough. So, what I normally do when I graph, okay, how do I know the biggest R will ever be is 1 in this problem? Well, the biggest cosine ever gets is 1, right? And the smallest it ever gets is negative 1. And if you square it, the biggest you can get is 1, right? So that's all you need here. So what we're going to do is we're going to plot a point every 45 degrees. Okay, so all you do is just plug in. Plug in 0. 1 squared is 1. Okay, plug in 45 degrees. Cosine of 45 degrees is 1 over root 2, and then you square it. 1/2. Okay, 90. Oh boy. 0. 0 squared is 0. 3 pi over 4. This is kind of ugly. Come on. Negative 1 over root 2 squared. Okay, people, if you cannot compute these values, you're in trouble. Negative, I gave it away already. Pi. Cosine of pi is negative 1, but then you got to square it. So you get 1. 5 pi over 4 is negative 1 over root 2, but you got to square it. Just like these two. Half. 3 pi over 2. Cosine is 0. Okay, good. You guys can square 0. 7 pi over 4 is 1 over root 2 squared. You get half. See how there's like a pattern? And then now please connect the dots in the order that you graphed them. Right? Don't just... This is like pretty much like a dot to dot now. This is like 1, 2, 3, 4, 5, 6, 7, 8, 9. Just dot to dot. But please don't connect them with straight lines either, because they don't go in straight lines, because as the angle sweeps out, it goes gradually from 1 to 1/2. It doesn't go like that, so it's more like this. So the graph looks something like that. Okay? So on the test, you will have one of these. Okay, let us do, you have to do 2D tonight. Okay? So I will do 2C.
We just do those.
Yeah, that's tonight's homework. And we're not gonna do 2A and B. No. 2A and B, because those are spirals, but those are actually fun to do, but we're on plan B already. R equal. So I'm gonna do 2, what did I just say? I forgot already, C. R equal cosine theta over 2. Okay, some of you might get confused in this, but we'll just see. 1, 1, 1. Okay, plot a point every 45 degrees. So plug in 0. No, the directions for this problem is plug in every 90 degrees. But then you got to go from 0 to 4 pi. You got to go 2 times around. Okay, plug in 0. People, if you cannot plug in 0, what's 0 divided by 2? And what's cosine of 0? 1. Keep track of the points on where you put. Maybe, you know what? Why don't we connect it as we go? Because then some of you are going to get confused, I know already, because R is going to become negative at some point. Okay, plug in pi over 2. What's pi over 2 divided by 2? Pi over 4. What is cosine of pi over 4? Yeah, but it's better in this case to know root 2 over 2, because we know root 2 is 1.4. 1.4 divided by 2 is 0.7. So 0.7 would be about there, yeah. See, when you're graphing, that's why you have to know root 2 is 1.4 and root 3 is 1.7. Otherwise, it's hard to draw graphs. Okay, pi. Okay. Pi over 2, cosine is 0. So it goes from here to 0 gradually, so it goes like this. Because you got to remember there's angles in between now. It doesn't just go straight down like that. Okay, where are we now? We're at 3 pi over 2. Plug it in. What's 3 pi over 2 over 2? 3 pi over 4. What's cosine of 3 pi over 4? Negative root 2 over 2. So it's going to be negative 0.7. So at 3 pi over 2, it's negative 0.7. So you got to go 0.7 the opposite way, so it's up there. So what happens is from here, it goes to there. See, this is where students always get confused when r becomes negative. Yo, Mr. Park, how do you know it goes like that? How come it doesn't just go back down? That's because, what about the angles over here? All of these angles here, r is negative, so you got to go on the opposite side, right? That's why it's over there. Okay, now we're at, where are we now? Well, we're at 2 pi. Plug in 2 pi. What's 2 pi divided by 2? Pi. What's cosine of pi? Negative 1. So that would be over here. It's on the opposite side. So from there to there. But then see, now we got to keep, see, it's not enough to go from 0 to 2 pi. We got to go 0 to 4 pi, so we got to continue. So 5 pi over 2. Negative root 2 over 2, which is negative 0.7, which is over here. So now it goes over here. 3 pi. 0, so it goes to 0. 7 pi over 2. There's positive root 2 over 2, so that would be here. So it goes like this. And then finally 4 pi. 1, no, it's 1. So there's 1. And there you go, that's what the graph looks like. See, so if you don't really understand polar coordinates, like when r becomes negative, you got to go on the opposite side, then it's very difficult. But I'm going to go easy on you on the test. I'm not going to, if you have to graph it by just plotting points, I'm not going to make r become negative because then I'll have breaks loose. So I'm going to make it like D. See, in problem D, can you see that r will never be negative? Because I added the plus 1, that's why. So then you don't have to worry about going on the opposite side. So that makes the problem much easier. Okay, what time is it? Oh my goodness, we're in trouble. Okay, next one. Now, this is just like when you, in Algebra 1. In Algebra 1, once you learn how to graph lines, what was the next step? Yeah, find where two lines intersect. So that's what we're going to do now. We know how to graph polar graphs. How do you find where they intersect? Well, okay, so I'm going to do A for you, and then you have to do B and C and then D. Yeah, D is a good problem, but then probably save down for the test, so you can practice it now. Okay, 3A. R equal 4 sine theta. Now, when you write this down, what are you thinking? That's a circle. Come on, you guys gotta know by now. And what is this? This is a rose curve with 4 petals, right? Okay, so the first thing we do is find where we're going to solve these equations algebraically. So what do? What do I do if I want to find where two graphs intersect? It rhymes with substitution. Substitution. If r equals this, you can substitute that for r. These cancel out. Okay, now how do I solve this equation? That's why we had to solve all those equations before. There's 3 identities for cosine 2 theta. Which one do I use? Since this side is sine. The one with the sine. Oh, so Mr. Park, we still got to know identities. Now, until you finish your math career, you must know all your trig identities. Otherwise, you're just going to keep relearning it every semester. In high school and college. Okay, and then you factor. No, I'm going to show you, Mr. Park. I'm going to quit that right now. No theta. 1 and 1 plus and minus. So sine theta is equal to 1/2 or -1. And see, these are all numbers we know. If it doesn't come out like this on the test, you're doing something wrong. You got to get 1/2, 1 zeros, root 3s over 2. Sine of what angle is 1/2? 5 pi over 6 and pi over 6. I don't know when they put pi over 6 first. Foolish. And then sine of what angle is -1? 3 pi over 2. Now, we have to find points of intersection. These are just the theta coordinates now. We just found the theta coordinates. How do I figure out the r coordinates? You plug it back into either one of these. Which one looks easier, A or B? I think A, huh? So if you plug in pi over 6, sine of pi over 6 is a half times 4 is 2. You plug in 5 pi over 6, 1/2 times 4 is 2. You plug in 3 pi over 2, -1 times 4 is -4. These are your points of intersection. Okay, now what we're going to do is now we're going to graph. Which you guys don't like, but in next year in BC Calculus, graphing is super important. Okay, this is a circle. Remember, this is last night's homework. What was the fast way to graph the circle? You just plot 2 points, 0 and pi over 2. If you plug in 0, you get 0. And if you plug in pi over 2, you get 4. 1, 2, 3, 4. So this is the diameter of the circle. The circle is right down yonder, right there. Okay, this is a rose curve. Since this number is even, you're going to have twice as many petals, right? So there's 4 petals. And since this is a cosine 1, you set the argument equal to 0. So theta equals 0. So that means at 0, you're going to have the first petal. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. So each petal is going to be 4 units long, all equally spaced apart. So it's going to look like this. So let's verify all the points of intersection. 2 pi over 6, check. 2 5 pi over 6, check. -4 root 3 over 2. So root 3 over 2 is this way, so you got to go 4 units in the opposite direction. Check. So check, check, check. Does anybody see anything else odd? Like, does anybody see any other points of intersection? Yeah, right here at the origin, look, the pole. Another name for the origin is the pole, right there. Can you see that both graphs intersect there? How come it didn't show up over here, though? That's because if you were to graph them, they don't get there at the same time. They get to the origin at different values of theta. So like if you were to graph the circle, it kind of looks like this. I mean, graph these graphs, it goes like this. You know, like that. And then, but they never get to the origin at the same time. So that's why it doesn't show up algebraically. But we can clearly see that the circle and the rose curve intersect at the origin. So what do we say? We say that the pole, remember pole is just another name for origin. The pole is a graphical point of intersection. And that just means the only way you can tell is by graphing it. You graph it and you can clearly see, yes, they intersect there, but it doesn't show up algebraically. That's why we call it a graphical point of intersection. Okay, now we've got 5 minutes to learn the other stuff. We're in trouble. We might have to make adjustments tomorrow. Now, is there like applications of polar coordinates? Yes, there's plenty. Okay, but one of the major ones is you can use it on complex numbers. Now, what is a complex number again? A complex number is a number of the form a plus bi. We call this standard form. See, this is the real part. This is the imaginary part. Now remember, what is a complex number? We talked about this in the first quarter. Instead of having the x and the y axis, we have the real and the imaginary axis. This is called the complex plane. To graph a complex number, all you do is you go A on the real axis, you go B on the imaginary axis. So it's kind of like this. This is A and this is B. This vector here is the complex number. A complex number is a vector in the complex plane. This is called standard form. But there is another way we can write complex form, and it's called, I'll just tell you, it's r kiss theta. R is the distance you are from the origin, and theta is this angle over here. Hey, that's polar coordinates, Mr. Park. Yes. R kiss theta. And kiss, you see this kiss? Kiss is simply an abbreviation for cosine theta plus I sine theta. That's what kiss stands for. That's because you can see from this picture, can you see that this is r cosine theta? And that's r sine theta. That's all it is. Okay, so what you have to be able to do is if I give you a complex number, you have to be able to put it in polar form. It's called this polar form, this is standard form. And the opposite way around too. So here, let's do some quick examples. What if you have 1 plus I? Write that in polar form. The simplest way to do it is just draw the picture. If you go 1 on the real and 1 on the imaginary, like this, if this is 1 and 1, how far from origin am I? What is this? That's root 2, right? And what's that angle there? Pi over 4. So to write this in polar form, it's simply root 2 kiss pi over 4. It's just like polar coordinates. It's exactly like polar coordinates, except you have the kiss there instead of a comma. That's the only difference. And then you have to go backwards. Like what if you have this? 2 kiss pi over 6. How do you change this back into standard form? Well, what does KISS stand for? That's an abbreviation for cosine pi over 6 plus I sine pi over 6. And we know this number. That's root 3 over 2. That's 1/2 I. Right? The I always goes with this one, and then if you distribute the 2, you get root 3 plus I. Okay, now, why do we do this part? Because now if you look in your notes, you're going to see why. That's because, I wish we had more time, but we don't. Okay, if complex numbers are in polar form, like you have this, 2 kiss 30 degrees and 3 kiss 60 degrees, when you multiply complex numbers together, all you have to do is multiply the 2 r's, 6, and then you just add the 2 angles. 30 plus 60 is 90. Finished. These theorems are very powerful. And then what about dividing? What if you had 6 kiss, 90 degrees, and you divide that by 2 kiss 30 degrees? Well, then you divide the r's. What is 6 divided by 2? 3. And then you just subtract the angles. 60 degrees. Boom, finished. And then here's the most powerful one. What if you had 2 kiss pi over 6, but then I ask you to raise it to the 6th power? This is called Demov's theorem in your notes. All you have to do is raise this to the 6th power. What is 2 to the 6th power? 64. And you simply just multiply that angle times that. And you get pi. Finished. Now some of you are going, oh, what's so good about that? Well, what if I give you this problem then? Root 3 over 2 plus 1/2 I, raise it to the 9th power. How long would that take you? You guys remember the binomial theorem? If you were to expand this, you would have 10 terms. You guys remember how to get the coefficients? Remember 9 choose 0, 9 choose 1, 9 choose 2. That would take you a long time. But look how fast it is to raise to a power. Just raise that to the power and multiply that. Done. Finished. This is a super powerful theorem. It's called Demov's theorem. Okay, we only have 1 minute left. Okay, now there is one other theorem. It's called the complex roots theorem. You know what? I'm just going to have you try it. Okay, just look at it and see if you can even apply it. If not, ask tomorrow. Okay, so I deleted a lot of problems, but I'm going to give you all the parts. Especially look at your notes. Look at the notes. Look at the complex roots theorem right there. This one right. Wait, that's not the notes. No, go back to the notes. Hey, where's the notes? Here, the notes page. Look at the very last theorem on the bottom. You're going to be glad I give you that formula on the test. It's called the complex roots theorem. Okay, the bell's going to ring already. Just try your best, and tomorrow we'll try to clear up everything.